Basic counting principles. So to solve these problems here, we're going to use a tree diagram and use multiplication principle. The question is, how many two-letter code words can be formed from the first three letters of the alphabet? No letter can be used more than once. So these little images here on the screen, as you can see, is just an example of how we can set it up, just to kind of give you an idea. If we are talking about the first three letters of the alphabet, we are talking about A, B, and C. So what we're going to do is we're going to set it up, A, B, C. A can be connected to B and C. B can connect it to A and C. C is connected to A and B. And when we count this, we have three groups, right? And we end up getting 6 outcomes. How do I know that's true? It's because we have 1, 2, 3, 4, 5, 6 possibilities. We could say that each group has, or each one of these has 2 in it, and there's 3 of them. And that gives me my outcome for this, okay? Now let's talk about B. B says, what if we wanted to know 4 letters in the alphabet in the first 4 and still can't repeat them? Well, again, each one's going to come out with 1 less than the group. If there's 4 here, then that means A can connect to every one of these because we can't repeat this A. So what I can do is now say, oh, well, I noticed this pattern here. I got 4 letters, right? And they all group off to 3. So this outcome would be 12. So let's go to example 2. Example 2 says 15 colleges of interest to a high school senior includes 6 that are expensive. The tuition's around $20,000 per year. 6 that are far from home, which is over 200 miles away, and 4 that are both expensive and far from home. So we're going to, the first question says, if the student decides to select a college that is not expensive and within 200 miles of the home, how many selections are possible? So we're going to determine this, and it's sometimes easier if you can draw out a picture, but let's label it. It says that we have a total of 15, right? So let's call the number of elements in this as U is equal to 15. That's my overall total. And then we're going to, let's call expensive, let's call it E. So we call this U, call it expensive E. So the number of elements in that E is going to be 6. And this one here is far away. Let's call it F. So the number of elements in F is 6. And then this is both. This one here, this is E and F. So what I'm going to do is say the number of elements of E that intersects F. And the word and goes with intersection, okay? Oh, and that is 4. Don't leave that number off. All right, so now that I know that, I can start solving for the how many selections are possible. So I look at it and I see that we have, we can draw out a picture if you'd like. But to find the numbers of E prime, so let's draw it out right. Let's just draw the best we can. Oops. Okay, so this whole entire box here is going to be U. And inside it's going to be the number of elements in E prime that intersect F prime. E prime tells me it's everything but E. Okay, so if I draw out my circles right here, and we call this one E, and then I draw this circle here that overlaps it and call it F, inside just this E part right here is going to be the E that intersects F prime. So everything inside this counts is going to be everything but F, okay? This one right here, I'm going to label it right here just because I didn't make it big enough. This is where E intersects F. right? They both share that part. And this section here is E prime, meaning that's everything but E, and it intersects F. So when we notice that we compose the colleges, they're not, they don't union, right? So therefore the formula we would use is the number of elements of E prime intersects F prime is equal to the number of elements overall minus the number of elements E unions F. Okay, so let's solve. Well, to find the number of elements of E unions F, because we don't know that just right off the top of our head, we're going to take the number of elements in E and we're going to add it to the number of elements of F. And let's subtract that to the number of elements of E intersects F. So what does that tell me? That tells me that my E is 6 plus the F is 6 minus the 4. So now I have 12 minus 4. That gives me 8. So now I know what E unions F is. It's 8. So let's take the E. So what I'm going to do now is we're going to find the prime, right? So to find that prime, we're going back to this formula right here. Okay. So to find the number of elements in E prime that intersects F prime, my U, which is 15, minus my E, and I wrote my, no, yeah, right there, unions is 8. So my answer is 7. So be careful with the notation and following your steps in here. Write a little messy sometimes and make a mistake. So B says, if the student decides to attend a college that is not expensive and within 200 miles from home during the first 2 years of college, and then will transfer to a college that is not expensive but is far from home, how many selections of the 2 colleges are possible? Okay, so now let's solve for this one. This one says that we're going to, we can use that same picture above because we're still working with the same numbers. We know that we have the number of far away colleges is 6, and we know the number of expensive intersects far away is 4. So now we're going to do the number of the E prime, the expensive prime, that intersects F, meaning that it doesn't include that. Well, we're going to take our N of F minus this here. So I got 6 minus 4, which gives me 2. And we can fill in these spaces up here in that diagram with that, solving for it. Okay, so now what I have left to do, I have the final thing. We're going to take N1 times N2, which is going to be the number of elements of E prime intersects F prime times the number of elements that E prime intersects F. And what do I have? I have 7 because we got it up there from A times that 2 is 14. And that is my answer. Example 3 says, use the given information to determine the number of elements in each of the 4 disjoint subsets in the following Venn diagram. Okay, so we are already given this here. It says that A is 25, B is 65, A unions B is 75, and then the whole entire total is 200. Okay. So now how many elements are shared between A and B prime? So it means we're going to find that intersection. So the number of elements in A intersects B prime is the number of elements that are A but not B, because this prime means that we're not including this. So here's our formula. To solve for that, we're going to take the number of elements of A that unions B, and we're going to subtract the number of elements in B. So when I do that, I know that it was given to us, right? 75 minus the B is 65. So my answer is 10. And you can come back and label this up here. That's 10. You can label this. Now let's solve for B. B says how many elements are shared between A and B. So we want to know the union or the intersection between A and B. So that formula is going to be the number of elements of A plus the number of elements of B minus the number of A that unions B, because we want to know their intersection, right? So what is A? A was given to us as 25, B is 65, and the intersection was 75. Or excuse me, the union. We're solving for the intersection, 75. So our intersection is 15. And again, you can go up there and draw that in the diagram. C says, how many elements are shared between A prime and B prime? So to solve for, let me look at C is A prime and B. Okay, so that means A is not included in this one. So we're going to use that formula of the number of the total minus the number of A unions B. Oops, hang on, backtrack. We don't want A. Remember, we're doing the prime. So what do we got here? We are solving for A prime that intersects B. So my formula here is going to be the number of elements of A unions B minus the number of elements of A. That makes sense because A is not included, right? So now that gives me 75 minus 25. And so now A prime that intersects B is going to be 50. Okay. Now let's go see D. D says how many elements are shared between A prime and B prime? All right, so this is going to be the number of elements in the total minus the number of A that unions B, because remember, since they're both primes, we're not including A and B. So that means we're going to take 200 and subtract 75, and my answer is 25. All right, let's solve for 4. You would like to make a salad that consists of lettuce, tomato, cucumber, and croutons. You go to the supermarket intending to purchase one variety of each of these ingredients. You discover that there are 11 varieties of lettuce, 3 varieties of tomatoes, and let me highlight that. 11 varieties of lettuce, 3 varieties of tomatoes, 5 varieties of cucumbers, and 4 varieties of croutons. How many different salads can you make? All right, so we got quite a bit going on. So how we can solve for this is we can just go ahead and we can call it 1, 2, 3, 4, or we can say NL for the lettuce, N T for the tomatoes, NC for cucumbers, NCR for croutons. Or even just call it 1, 2, 3, 4. So what I'm gonna do is I'm gonna take 11 times 3 times 5 times 4. So what I get 33 times 20 gives me 660 different choices that I can make on my salads. All right. Example 5 says the management selection, a corporation plans to fill 2 different positions. We have a vice president, V1 and V2 from administration office in 2 of its manufacturing plants and plant A has 2 officers at plant B has 8. Okay, so this question here needs to finish out. We're actually right here needs to have and B, plant B. We're factoring them both. All right, so sometimes reading application problems, it just kind of gets a little messy, so we have to go back and reread it, and that will be helpful. Well, part A wants to know if the V1 position is filled from plant A and from plant B. We want to know what that answer is. So let's look at it. Plant A, V1, has 6 ways, right? That was given to us. V2 says it has 8 ways. So in order to figure out how many positions can this be, we're going to actually just take those 2 and multiply them together. And out of those 2 options, out of those 2, plant A and B, we end up with 48 positions that can be filled. B says, if the selections are made without regard to plant, the first position can be filled in 14 ways. All right, so if the selections are made without regard to plant, the second position can be filled in 13 ways after the first position is filled. So what do I have? I have 14, but after the first position is filled, I now have 13. I can multiply those 2 together and I get 82 ways, or 182 ways.